So again, I have come, your physics sir, Dr. Arko Chaudhary. So what we have ended was that Planck's law could successfully describe the black body intensity of black body distribution with lambda. That is, it was shown that the for that is for higher wavelength, case 2, for higher lambda tends to 0, it becomes the Wien's empirical formula, and for lower wavelength it becomes the Rayleigh-Jeans formula. So at lower wavelength, Rayleigh-Jeans formula doesn't have a so sorry, at lambda tends to infinity, it becomes our Rayleigh-Jeans formula. At higher wavelength, the Planck's radiation formula becomes the Rayleigh-Jeans formula. So at the higher wavelength, Rayleigh-Jeans formula didn't have a problem. It had a problem for lower wavelength only. And for higher wavelength, it matches with the E lambda versus lambda curve. Now at lower wavelength, what happens? At lower wavelength, it is seen by all these approximations. It turns out to be, it becomes actually the Wien's empirical formula. So again, the Wien's empirical formula again has no problem at lower wavelength. At higher wavelength, it has problems. So this problem is actually solved. Okay, so now we'll do how the actually from here quantum physics starts. Means from Planck's law, the quantum physics starts. Means how Planck described or removed all the discrepancies of the Rayleigh-Jeans law, that is the classical theory, and from here the quantum actually starts. The questions will definitely also come from your those part also, that is before Planck's law, but here the quantum starts. Okay, so now before this there are two very important laws, that is Wien's displacement law and the Stefan-Boltzmann law. So they are also again described by the classical consideration only. So now how will that change actually? How will that change by the application of this Planck's radiation law? So deduction of Wien's displacement law, and Stefan-Boltzmann law from Planck's radiation formula, So how is this done? Okay, so first one is Wien's displacement law. First one is the Wien's displacement law. And these are basically, again, these are all mathematics only. Okay, so Wien's displacement law is what? Where that is in that E lambda by lambda curve, you get a maximum lambda. That is this one only, means E lambda versus lambda curve, you get this. This is the point where you are getting the maximum E. It's called as lambda m. So you have to find it out. So U lambda d lambda is equal to what? 8 pi hc by lambda to the power 5 into 1 by e to the power of hc by lambda kt minus 1 into d lambda. Okay, so again, this is what energy density of radiation. So if you want to convert it into intensity of radiation, so E lambda is equal to c by 4 into U lambda. So from here just you have to do c by 4. So 2 pi h c square by lambda to the power 5 into 1 by e to the power of hc by lambda kt minus 1. Okay, this will be the thing. Okay, so how you can write this? You can write it like this: 2 pi h c square by z where this z is what? Z is actually this thing, this entire thing, because you are concerned with this only. Others are all constant. 2 pi h is constant, c is constant. C is the velocity of light. Okay, so z is this. Achha, now what you have to find, that is I mean lambda m is what? The wavelength for which E lambda is the maximum. So when will here when will E lambda be maximum? When this is minimum, z is minimum. Okay, so for z to be minimum, dz by d lambda must be equal to 0. So what is this dz by d lambda? So if you do the derivation, you can remember also, for the exam purpose you can remember, then that will be better for you. You don't have to derive and waste time there. Exponent 5 lambda to the 4 exponential of hc by lambda kt minus 1 minus lambda to the power 5 hc by lambda square kt into e to the power of exponential of hc by lambda kt is equal to 0. Okay, is equal to 0. So so now what will you get? So from here you will get 5 lambda into exponential of hc by lambda kt minus 1 minus hc by lambda kt into exponential of hc by lambda kt. Okay, this is equal to this. If you take lambda to the power 4 common, so this will come, right? So from here what will you get? You will get this 1 minus you will get 1 minus exponential of hc by lambda kt. You are taking here from exponential hc by lambda kt, you are taking common. So if you take common, it will be 1 minus exponential lambda kt is equal to here here exponential hc by lambda kt, here exponential hc by lambda kt will cut. So this will be hc by oh, here there will be no lambda here, I had written wrong. Hc, but this will be hc by kt here. This will be hc by kt. This will be hc by kt here. This will be lambda square. This will be lambda cube here. Then means this will lambda 5 and this was lambda square. So lambda square by lambda, this is lambda cube. So lambda cube if you take common, so this will be lambda cube you take common, so there will be 5 lambda expression hc is equal to hc what is happening here? You are taking here lambda cube hc lambda cube. Okay, you divide this both sides by lambda cube. So what you will get here? 5 lambda expression hc by lambda kt minus 1, and here you are dividing it. This is equal to so the lambda cube. So this will be hc by kt only, hc by kt exponential. It's all right. So and here you are doing you can take here exponential lambda kt, you can take common. So exponential lambda kt 1 minus exponential hc by I mean rather say you are dividing both sides. You are dividing both sides by exponential of lambda kt, hc by lambda kt. Okay, so you are dividing both sides by exponential of hc by lambda kt. So if you divide it, this is 1 minus, this is 1 minus, here will be 1 minus here. Okay, and this is the cut. This is hc by 5 lambda kt. Okay, hc by 5 lambda kt. So so this hc, here also you are getting hc by lambda kt, here also you are getting hc by lambda kt. So let hc by lambda kt is x. Okay, so here let hc by lambda kt is equal to x. So from here what will you get? 1 minus exponential of minus x is equal to x by 5. Okay, see here, 1 minus hc by lambda kt is x, 1 minus exponential minus x is hc by lambda is equal to x by 5. Okay, so now this is a very interesting thing. Again, this equation is called as the transcendental equation. This equation is called as a transcendental equation, where you have encountered this before in the diffraction chapter. Okay, so this can be solved only, this cannot be solved mathematically. It can be solved only graphically. It can only be solved graphically. Okay, so how it will be solved? There will be two equations. Okay, one will be y is equal to x by 5, another one will be y is equal to 1 minus e to the power of minus x. Okay, so these will be the two equations. So now if you plot y versus x, if you plot y versus x, what will you get here? Y is equal to x by 5, this is y and this is x. If you plot y versus x, so this will be y is equal to x, and y, another y is e to 1 minus e to the power minus x. So another one will be this one. So this will be y is equal to 1 minus e to the power of minus x, and this will be y is equal to x by 5. Okay, so the point of intersection, what will be the solution? One will be the point of intersection between these two graphs will be the solution. One will be this, means x is equal to 0, another one will be this, and the value of this is x is equal to 4.956. okay, 4.956. so x is equal to 4.956 means what is x here? X is hc. See here, x is hc by lambda kt. So hc by lambda kt, or you can tell that this definitely this will be lambda m only. For that you are getting the maximum e lambda. Hc by lambda m kt is equal to 4.956. so from here what will you get? Lambda m into t is equal to hc by 4.956 into k, where k is the Boltzmann constant. K is the Boltzmann constant. Its value is what is its value? 1.38 into 10 raised to minus 23 joule per Kelvin. Okay, so if you plot, you know the value of h, you know the value of c. So if you do, it will be 0.29 into 10 raised to minus 2 meter. Okay, and 10 into 10 raised to minus 2 meter. So this is the Wien's displacement. This is the Wien's displacement law. Okay, so this constant lambda into 2 is equal constant. You can tell it, say c or something like this. So this constant is same, 0.29 into 10 raised to minus 2 meter. Now at the beginning, when I have done the see here, 2.898 into 10 raised to minus 3. So I mean this is actually 2.898 into 10 raised to minus 2. Sorry, 2.9 10 raised to minus 3. So this is actually you can write it like this, that divided by 10 into 10, so point 289 into 10 raised to minus 2. Okay, so this is the same as this thing. This is the same as this thing, that is 0.29 into 10 raised to point, that was 0.2898, so that is 0.29 only, 0.29 10 raised to minus 2 meter. Okay, then comes your the proof of the Stefan-Boltzmann law. Proof of the Stefan-Boltzmann law. Proof of the Stefan-Boltzmann law. So how will you prove the Stefan-Boltzmann law? What is the Stefan-Boltzmann law? The total the total energy density U of radiation, the total energy density U of radiation is what? That is equal to, U is equal to, will be integration of 0 to infinity within the frequency range. This is U nu d nu is what? U nu d nu is the only the energy density of radiation in the frequency range nu and nu minus d nu. So total energy density of radiation within the entire frequency range will be what? 0 to infinity. Okay. Now what is that actually? I mean, that is E lambda, na? That is here total emissive power, that is total emissive power, that is emissive power, or you can tell it E lambda as the total intensity of radiation also. So E, how will you calculate E? E will be C by 4 into U. So for that you need to calculate the total U. So I will calculate like this. So U nu d nu. So what will be this? This will be integration of 0 to infinity 8 pi h by c cube into nu cube d nu by e to the power of h nu by kt minus 1. Okay, so here if you substitute h nu by kt, if you take it as x, okay, if you take it as x, so what will be u? U will be equal to 8 pi h by c cube into kt by h whole to the power 4 integration of 0 to infinity x cube dx by e to the power of x minus 1. Okay, so now this x cube dx, okay, x cube dx is equal to this thing, this thing you can, this is a what to say, that is a integral of I mean the pi function, involving pi function, all those things. You can directly write this as you can directly write this as pi to the power 4 by 15. You can directly write this as pi to the power 4 by 15. So this will be what? This will be 8 pi h. It will be definitely it will be 8 pi into 8 pi h by c cube into kt to the power 4 by h to the power 4 into here pi to the power 4 by 15. Okay, so here h by say h cancel, this will be h cube. So this will be 8 into pi to the power 5 into k to the power 4 into this, here there will be t to the power 4 by c cube into h cube into 15. Okay, 8 pi k to the power 4 into t to the power 4 into 8 pi to the power 5 into k to the power 4 by c cube into h cube. Okay, so this is a constant called as the sigma, or the sigma is the what, the the Stefan Boltzmann constant. Sigma is the Stefan Boltzmann constant. Okay, so this is the thing. If you now calculate it, so I mean this will come out as this sigma. Then actually you have to find out E. So E will be what? E will be C by 4 into U. Okay, so I mean to that constant one, that is the constant was what? Constant was 8 pi to the power, here first 8 pi to the power 5 k to the power 4, 8 pi to the power 5 k to the power pi to the power 5 k to the power 4 by c cube h cube 15 c cube 15 c cube h cube. Okay, so here you have to multiply, just you have to multiply it by c by c by 4. Okay, and already there is t to the power 4 is already there. So here this will be c square, and here this will be 2. So this constant will be what? This constant will be 2 into pi to the power 5 into k to the power 4 by c square h cube into, it will be t to the power 4. Okay, into t to the power 4. So 2 pi to the power 5 into k to the power 4 by c square. Oh sorry, there is one 15 also, 15. 2 pi to the power 5 into k to the power 4 by 15 into c square into h cube. Okay, so this is the constant. Sorry, that was not the constant. Actually, this is the constant. Okay, because that was only u. So this is not the constant. This is not the Stefan Boltzmann constant. Okay, this is not the Stefan Boltzmann constant, because that is in terms of u. Stefan Boltzmann constant will be in terms of e. Okay, so this is actually the Stefan Boltzmann constant. Stefan Boltzmann constant, and its value comes out, if you do its value will come out to 5.67 watt per meter square per Kelvin to the power -4. Okay, so again this is the same. I mean 5.67 watt per meter square Kelvin to the power 4. This is the same as this, say 5.67 watt per meter square per Kelvin to the power -4. So here constant Stefan Boltzmann constant comes out as 5.67 in watt per meter square per Kelvin to the power -4. So this is this only. So E is equal to sigma into t to the power 4. This is the Stefan Boltzmann law only. This is the Stefan Boltzmann law from the Planck's distribution law. So this kind of questions come in the exam. Very big question. First of all, that prove the Planck's radiation law. That is u lambda d lambda is equal to 8 by 8 c by lambda to the power 5 1 by e to the power 8 c by lambda kt minus 1 into d lambda. Prove this thing. Prove this thing. Prove the Planck's radiation law. Then from that, show that for lambda tends to infinity, for high lambda, Planck's distribution law becomes the Rayleigh-Jeans law, and that low lambda, that is lambda tends to 0, it converts to the Wien's displacement. It converts to the Wien's empirical formula that you have to prove. The big marks or five marks question can come, and then show the Wien's displacement law from the Planck's distribution law and show the Stefan Boltzmann law from the Planck's distribution law. Okay, so these kind of questions can come. So now the god of physics, that is Einstein, came into the picture now. Einstein's concept of Einstein's concept regarding black body radiation. Okay, Einstein's concept regarding black body radiation. Now, what did Einstein conceptualize? He said that just like the energy of the oscillators are quantized, okay, electromagnetic radiation is also quantized. Okay, electromagnetic, this was only his assumption, that just like the energy of the atomic oscillators is quantized, the electromagnetic radiation is also quantized, and it is quantized in the form of the energy packets, that is h nu. Okay, so so according to Einstein's assumption, according to Einstein, the electromagnetic field itself is quantized. Electromagnetic field itself is quantized. Okay, just like the energy of the atomic oscillators, okay, the electronic field itself is quantized just like the energy of the atomic oscillators, and light consists, light means electromagnetic radiation only, light consists of energy packets, or particles. Light consists of energy packets or particles known as photons, each of which travels with a velocity of 3 into 10 raised to 8 meter per second in free space. The energy carried by each photon is given by E is equal to hc by lambda, or is equal to E is equal to h nu. Okay, and since the black body radiation is actually a photon gas, okay, and black body radiation is actually a photon gas, in thermal equilibrium, with the atoms on the walls of the black body cavity. Okay, So according to Einstein, electromagnetic field itself is quantized. Electromagnetic field itself is quantized, just like the energy of the atomic orbital, and light consists of energy packets or particles known as photons. Okay, light consists of energy packets or particles known as photons, each of which travels with a velocity of 3 × 10⁸ meter per second in free space. The energy carried by each photon is equal to h nu. Okay. So now what happens is that I mean this is actually the I said that quantum mechanics is for microscopic particles. Okay, quantum mechanics is for microscopic particles. Now for microscopic particles, what happens is that for microscopic particles, it is traveling, these these particles are traveling with a speed very high, that is speed of the velocity of light. Okay. Okay, so what happens when they are traveling with a speed, they can be regarded, they can be regarded relativistically. Okay, so what happens when a particle travel with the speed of light, okay, then its mass changes. Okay, then its mass changes. This is called as relativistic mass. This is called as relativistic mass, and it is given by m is equal to m naught square root of divided by square root of 1 minus v square by c square, where m naught is equal to rest mass of a body, rest mass of the body, that is the mass of it when the body is at rest. Okay, so its mass changes with the relation to, these are relativistic particles. For macroscopic bodies, the mass of a bus, that is SBSTC bus, does not change. The mass of you when you're running in the football field, your mass doesn't change. Okay, but mass of the electron, proton, photon, which are relativistic particles, they travel with the velocity of light. Okay, they travel with the velocity of light. So that mass actually changes with the relation like this: m is equal to m naught by square root of 1 minus v square by c square, where v is its velocity and m naught is the rest mass of the body. Okay, m naught is the rest mass of the body. Okay, so thank you.